Welcome to the trial lesson for the iGCSE Chemistry with South West Science School. Working through this will give you a really good indication of the level of work and the content that we'd be doing to complete the GCSE over 2 years, including school holidays. So every week you'll work through a lesson like this, and you can do it at your own pace, and after it you should be in a really good position to complete any of the assignments. The trial lesson is actually a real lesson. It's taken from about 5 weeks into the course, so 5 lessons in. So don't be worried if there's a couple of things that you don't feel you quite get yet, because we will have already covered them. This iGCSE is taught to, well, all the iGCSEs with us are taught to A star star, which is like the new level 9 on the new syllabus. But it also goes back and tries to fill in the gaps as if you didn't have any previous scientific knowledge. So the courses are very thorough and quite content heavy. Today we're going to be improving our pirate skills a little bit by learning how to make rum and also turn seawater or urine into drinkable water, so we can dehydrate ourselves with all of our rum and then hydrate ourselves back up again with our own wee. Excellent. The way we're going to carry out these pirate tasks is using distillation. In particular, 2 types of distillation we need to learn for our iGCSE. They are simple and fractional. We'll start with turning seawater into drinkable water. I hope you're never stuck at sea in a dinghy, but if you remember this lesson, it could save your life. Okay, we've already looked into the processes of evaporation and condensation the other day when we made our own clouds in a jar, but I'll recap because without knowing what these 2 things are, you're not going to get very far in turning your salt water into drinking water, or at least understanding why it happens. So basically, when we heat a liquid like water, if we heat it up enough, it boils and it releases steam. Simple enough. We call it evaporation. The liquid is turning into a gas, steam. Condensation is the complete opposite of evaporation. It's when we cool the steam and it turns back into liquid water. So it's steam turning back to water. You see condensation in your shower with those little droplets on the curtain or the panel. The water was so hot when it created steam in the shower, it evaporated and then it sort of travelled to the curtain or the panel and cooled down because of the air on the other side of the shower, and it turned back to liquid, turned back into these little droplets. So evaporation and condensation are the key players in turning seawater into drinking water. So the picture on your right shows you how you're going to make this happen, how you're going to make your drinking water. You need to get a container of some form. You place salt water in it and then place an empty cup in the center. Now you need to evaporate the water. Evaporation needs heat. Obviously a fire or a Bunsen burner are going to give you much more heat, but if you're stuck on a dinghy, the sun is going to have to be enough. Let's just hope that you're stuck in the Caribbean or something. So the sun heats the salt water and the water evaporates. So you're going to need to cover this to catch your water, else it would just evaporate into the air and all your effort would just be pointless. So you place something over the container of seawater. Cling film would be good, a plastic bag, even tarpaulin, but it must be a tight fit and it must dip slightly in the middle. A tight fit because we don't want all of our evaporated water escaping, and dipped because we want all the water to drip into the cup in the middle. You don't want it to just drip back into the bowl. So to make a dip, you could just weigh it down slightly with pebbles, sands, a bit of jewellery, anything, just to direct those drips into the cup in the middle. And voila, you should get clean drinking water. It might take some time, depends on how hot you get it, but it will work. Now the reason it works is because water boils at much lower temperature than salt, and we call this its boiling point. Water's boiling point is 100 degrees Celsius, but a salt's boiling point is nearly 1,500 degrees Celsius. So it was never going to evaporate in your little dinghy setup. The water was always going to evaporate first. The water evaporates, sticks to the cling film, say, or the plastic bag, Cool air on the other side condenses that, turns into little droplets, travels down into the middle because you've created a dip, and then drips into your cup and gives you some drinking water. So to recap, our seawater, our salt water, is the sort of blue liquid at the bottom of the larger container. Heat it up in the sun with a covering over the top that's got a little rock or something weighing it down so it dips in the middle. Sun heats it up, the air inside this little container we've made gets really, really hot, it heats the water evaporates. As it rises, it hits the cool air, it comes into contact with the cool air above it, condenses, so it turns back into a solid, turns back into water, drips back down into the middle, and hopefully drips into our empty cup, which is the white one in the middle. This eventually will evaporate all the water, because in salt water that is all there is, that's all there should be, salt and water. So the heat will eventually evaporate all the water and you'll be left with just a salt at the bottom of your large container, which would look a little bit like the picture in the bottom left. So that was the standard way that you would probably try and turn salt water into drinking water if you were trapped at sea, because you'd probably have very little equipment and materials available for you to do it. But there are other ways that people and humans have done it in the past. The picture on the right is actually they call it a solar still. It's essentially what we've just been doing. It's solar, is the sun, so they're using the sun to turn seawater into distilled drinking water. It's something you can buy. It costs about £130. You can buy it on Amazon. It folds up into a little neat bag that you could put in your suitcase. You never know when you might need one of these, but essentially it does exactly the same thing. You pour some seawater into the bottom, it heats up in the sun, the water evaporates, condenses when it gets to the top. Unlike ours, which had a dip in the middle, encouraged all of our drinking water to fall into a cup in the middle, this one has a peak at the top, so it will encourage all of that water to drip down to the sides, and then you can drink all of this fresh water. Another example that was used for people who had access to fire and land is this one on the left. Basically, you get a big pot of your salt water and put it over a fire. So it's going to heat up, the salt water is going to heat, the water is going to evaporate, but instead of being caught in another container, the water evaporates into a really thick cloth hanging over the pot, and it will all condense into this thick cloth when it hits the cool air above it, and then you can just take that cloth and wring it out into another bucket or another container, and then you can drink it. Distillation is a process that we use to separate out solutions. If you've gone through any Key Stage 3, maybe actually probably even Key Stage 1 or 2, you may know what a solution is, but I want to clarify this now because just occasionally they do actually go back and ask some questions on it. So a solution is when we have a gas, a liquid or a solid dissolved into a different gas, liquid or solid. Normally it's a solid dissolved into a liquid. We call it a solute, is the thing being dissolved. The solvent is the thing that it's being dissolved into, and the solution is what you get at the end. Spend a bit of time just getting around those words and not getting them mixed up, because it is easy to mix up solute and solvent. There is generally a lot more of the solvent, the thing that something's being dissolved into. There tends to be more solvent, and the solvent tends to be water a lot of the time. In our example, in our distillation processes that we've been just going through, the solution is seawater, salt water. The solute is the solid salt, and the solvent is water. So in seawater, as you might guess, there is a lot more water than salt in it, a lot more solvent than salt. Okay? Distillation is crucial because it's separating out things in a solution. It's trying to get a liquid away from its solid. Now we've already done separating out of other substances, such as trying to get the solid out of something. If you look at the apparatus, if you look at the setup, the experimental setup in the blue box on the right, you'll see something quite similar to what we've already been doing. However, it doesn't have a roof, it doesn't have a lid, it doesn't have a piece of plastic above it. This is crucial to distillation because we want to catch that liquid, we want to catch that solvent coming away from the salt. If that wasn't there, like in the case of that picture, all the water would evaporate and you'd be left with salt, which is great if you want the salt, but distillation is trying to separate out the liquid and keep it. So essentially what you have been doing is a process called distillation. You have been making distilled water. And you've been making distilled water from seawater, but you can make distilled water from other things. It doesn't just have to be salt water. A good example of that would be dirty water that you might see in a stagnant pool or a dirty pond. You can do exactly the same principle, cover it up, get some heat onto it. It should evaporate the water and leave all the rest of the dirty stuff that we don't want. It should hit some sort of sheet above it, like you've got in the picture on the left, condense when it touches the cool air, and then drip into a container, exactly like it was before. Now, when you're dealing with dirty water, you do have to be a little bit careful because you're not positive that the water that is evaporating is just water on its own. There could be some microbes, some bacteria in there that might not be good for you, but obviously it's something you could use in an emergency. Another one that you can use is you can even draw the water out of the ground or plant material. So you could create a dip in the ground a little bit like the one here, and as long as the ground is quite moist or there's lots of vegetation, lots of plant matter in that dip, you could heat it up and still get drinking water from it. Distilled water is not just for survival. We actually make it in our everyday life. We make it in industry, we make it in factories, and it has lots and lots of uses because sometimes we need to know that what we're putting in something is actually water. It's not got other bits and bobs in it. When you put your tap on, it'll have quite a lot of chlorine in it because we'd have put chlorine in it to keep it clean. It might have some other minerals in there or some metals depending on the pipes that it went through. And sometimes we really don't want all those things in it. We want to know that it's just water, hydrogen and oxygen, water. And some of the things we might use that for would be cooling systems in your cars. If you need to put water in your car, you should try and use distilled water. Over a period of time, some of the metals in water can actually corrode parts of the engine, so distilled water is better for that. We need it in science. We use it in experiments because in science, we really want things to be accurate. We want our results to be reliable, and we want to be able to tell people that the results we've got due to some water substance in there is actually due to the water, not due to something else that could be in there. Surgery is another good example. Any sort of cleaning that would be required in doctors, in medicine, when they're doing a operation on you, they don't want to be putting things like microbes and bacteria into their body. They want to know that it's actually really water that's cleaning you. Now, you don't need to know some examples of distilled water in some uses of distilled water for your exam, but it puts things into perspective a little bit about what you're doing and the process of distillation. So we've learned quite a lot of different little snippets of information that we need to start bringing together. So we're going to do a little learning check. For the first exercise, I would like you to look at the composition, which is the what is in basically, of urine, of wee. So on the right hand side, you will see pretty much an average composition of urine. Most of it will be water, 95% of it will be water. and the rest will be different sort of magnesium, calcium, potassium, urea, ammonia. That's what gives it that lovely smell. For your first exercise, I would like you to look at this chemical makeup, look at this composition of urine, and I would like you to write down the solute or solutes, the solvent or solvents, and the solution or solutions. So it's just practicing whether you know the difference between solute, solvent, and solution. For exercise 2, I would like you to pretend that you are lost in a desert and you have no water. You need to design a piece of equipment to turn your urine, your wee, into drinkable water. And all you have with you is a plastic bag, a knife, a plastic drink bottle, and yourself and the natural landscape, the natural desert landscape around you. We have been distilling water from dirty water. We've been distilling water from seawater. There should be no difference distilling urine. We're trying to get the water out of urine. We're trying to get some drinkable distilled water from urine. I'd like you to design the piece of equipment that's going to do this. Pause the video, and when we restart, we'll go through the answers. Going through exercise 1 first, we need to break down urine into its solute, its solvent, and the solution. So I hope you all got this right. The solution is going to be the urine. It's what everything mixed together is called. Urine is the solution. The solute is the something we have less of. And generally, it's a solid. But it can be a gas or a liquid as well. The solutes in urine are all the things that I've put a little square around, a yellow square around. So the ammonia, the sulfate, the phosphate, the chloride, the magnesium, all of them are solutes. And we know that because all of them collectively together are lower. They're the least thing in the substance. The solvent is water. If you see water in a question like this that asks you to say what is the solution, what is the solvent, what is the solute, and water is present, and the majority of the substance is water, the solvent will always be water. Water will be the solvent. So in exercise 1, you were asked to find out what the solute, the solvent, and the solution are in urine. I've put them into boxes. The yellow box is the solute, it's the ammonia, the sulfate, the phosphate. The blue boxes are your solvents, it's your water. The majority of this is a solvent, it's water. And then altogether, the solution is everything mixed, urine. I hope you had some fun with exercise 2. Essentially what you are going to do is draw a very similar picture to what we've already been drawing quite a few times in our distillation of salt water or dirty water. You wanted to have some sort of pit, possibly dug out with your bare hands. We could have used some of the plastic bag to line that pit. We could have cut our water bottle in half and placed it in the bottom of that pit, and then poured our wee around it, covered it, put a little dip in the top, maybe some jewellery or something that we had on us, some sand, some dirt, so that the urine would then heat up, the water from it would evaporate up, reach the sheet at the top, which would hopefully be a little bit cooler than what's inside you've created, and then roll down and dip into your cut down plastic bottle. It's possible that you came up with a different idea, a different method, and a different set of equipment and apparatus to distill your urine into clean fresh water, but essentially that would have worked, or anything that we've said in the previous slides would have worked. Now I'd like you to watch this lesson's extra video. It will be below this in the trial on the website. and it is a Bear Grylls video where he does just this. He turns his wee into drinking water. When we want to separate one liquid, so one solvent from its solute, we use the process called simple distillation. That is what you have been using so far to clean your dirty water and to separate your water from your seawater, salt. So simple distillation is when you're separating out one liquid from the solution. When you have lots of liquids mixed together, we use a different type of distillation, and that's what we're going to move on to next. But simple distillation is something that you need to know for your iGCSE, and it's separating one liquid from the solution. We went through it before, but this little picture on the left at the top just shows you how much you need to have a cover on. This is the difference between separating out a solid from a liquid. If I just want to get the solid, if I just wanted the salt, then I could just literally heat the bowl of seawater and let all of that water evaporate away, because I wouldn't want it. But with simple distillation, I want to keep that water. That's the point. I'm trying to separate out the liquid. All of the things that we've been doing are pretty crude. They're things that we would do in a survival situation. But in a laboratory, in a factory, in industry, we wouldn't be getting a plastic bag and a pair of earrings. We would have special chemistry equipment. And the equipment that you would use in simple distillation is shown in the bottom left blue box. So you have this sort of round sphere ball-like glass. That is where we would put our seawater. We would have a thermometer stuck into the top of that, and it would be sealed, so it would get nice and hot really quickly when we heated it with a Bunsen burner from underneath, or a furnace, or any sort of heat source that was stronger than the sun. So we turn on the heat source, the seawater would bubble, and the water would evaporate off when that thermometer reached 100 degrees centigrade, which is the boiling point of water. Then all of the evaporated gas, the steam from the water, would go down a condensing tube, a condenser. This is the thing sort of poking out from the right hand side, and you can see there is a darker blue on either side of the condenser, and that's because condensers quite often have cool liquid pouring around the outside. Now we know if water's evaporated, and we know to make it evaporate we need heat. But to condense it and get back it into a liquid again, which is what we want because we want to drink it, we need to condense it. And that's why it's called a condenser. It cools down all of that gas back into a liquid so that we can drink it. A condenser might not have a cool liquid around it. It might just rely on the cool air. But either way, that's what it's doing. It's trying to cool down all of that gas back into a liquid again. The problem with simple distillation is you can only separate out things. You can only get things that have very different boiling points. So when we were talking about salt and water from our seawater, the salt had a really, really high boiling point, which meant you'd have had to heat it up to temperatures of 1,500 degrees centigrade to get that to evaporate. The water evaporates at 100 degrees centigrade, so that's a really big difference in their boiling points, and that's when simple distillation comes into play. If we want to separate out lots of different liquids from a mixture, and all of those liquids have boiling points that are very similar to each other, then we need to use a different type of distillation. Before we move on to this more complicated type of distillation, I'd just like to do a little learning check to make sure that you understand the simple distillation first before we move on. So about 2 videos down from here will be another one called Simple Distillation. I'd like you to watch it and then answer these questions as you go through. Pause this video first so that we can go through the answers together in a second. So we're going to go through the answers now. How does the water condenser work? Well, condensers are not always water condensers. They are in this case because they're condensing water, but to be honest, they can condense any solvent from the solution that is evaporating and needs condensing back again. The condenser is that little piece of equipment that was stuck out to the right. So when the acetone evaporated, it would go travel into that condenser and hopefully be turned back from a gas back into a liquid again. Number 2, what is so special about 56 degrees centigrade for acetone? 56 degrees centigrade is the boiling point of acetone. Boiling points are crucial for distillation because we know that when that thermometer stuck in the top of all this equipment reaches 56 degrees centigrade, we know that the acetone is now boiling and is actually evaporating. So we know that all the steam collecting inside is acetone. Number 3, the boiling point of water is 100 degrees centigrade. You should probably know that already. It's fairly common knowledge, but if you don't, you need to get that one in. I think that in an exam they would expect you to know that. They would never give you that information. Question 4. Explain why acetone ends up in the beaker and water in the distillation flask. Use the term boiling point. Okay, so acetone has a much lower boiling point than water. Acetone's boiling point is 56 degrees, water's is 100. So when it reaches 56 degrees, which it will do first, the acetone is going to evaporate. The acetone is going to evaporate a lot sooner than the water. It will leave the water at the bottom of the distillation flask, you know, that big round ball-shaped flask, and the acetone is going to rise up. Therefore, it will condense sooner and will collect in the beaker sooner, leaving the water still trying to reach its boiling point in that flask. We're going to move on to now that slightly more complicated type of distillation, which is called fractional distillation. Simple distillation separated out one liquid from a solution. Fractional distillation can separate lots of liquids with really close boiling points. In an exam, when they talk about fractional distillation, I would 95% say that they're going to be talking about crude oil or ethanol and water. You need to learn these examples. We're going to be moving on to crude oil in a lot more detail when we do a lesson on how to make rocket fuel using fractional distillation. But you need to know that it's more than possible that you will get a question that asks you which one of the following is an example of fractional distillation. And trust me, the two that will be there will be crude oil or ethanol and water. Ethanol is alcohol, so any sort of alcohol and water is possible, they might say that. But crude oil and ethanol and water are the two examples of fractional distillation. Similarly, for the simple distillation that we've just been doing, 99% likely it's going to be seawater, salt water, that is going to be your example. So if they ask for an example of simple distillation, you say salt and water, salt water. If they ask you an example of fractional distillation, you can either say crude oil or ethanol and water. Don't say rum or vodka or gin, ethanol and water. Right, fractional distillation is really not that much more difficult to learn because it uses almost identically the same equipment as the simple distillation. If you look at this diagram, there's not a lot in it. You have this round flask at the bottom as usual that we fill up with the solutions that we want to separate out. We heat it from underneath with a Bunsen burner. There's a thermometer in the top so we can tell which one's coming through, which one's reaching its boiling point. There's a condenser on the right that's cooling all of that evaporated gas down and making it into a liquid again. But we have one thing added, and it's called a fractionating column. Take that one in, write that one down, learn it. Fractionating column. That is the only difference in the pieces of equipment between fractional distillation and simple distillation. Fractional distillation has a fractionating column, and I've highlighted it here with a red arrow. It is just underneath the thermometer, and it's a long tube that's often filled with things like glass beads. And the point of it is that it is cooler at the top and hotter at the bottom, which makes sense. It's hotter near the heat source, but all these glass beads are aiming to create a much stronger temperature gradient. So it's much cooler at the top than it is at the bottom. This is crucial and another aspect that you will need to take in. A fractionating column is cooler at the top and hotter at the bottom. I will put all this in your exam summary sheet, so you don't need to go taking notes like crazy, but please take it in that the difference between simple and fractional distillation is the fractionating column, and the fractionating column is cooler at the top and hotter at the bottom. And this is one of the key reasons that it is capable of separating out lots of different liquids in a mixture. Say we have 3 different liquids in the mixture and their boiling points are reasonably close. The one with the lowest boiling point is going to start boiling at the lowest temperature. So this one's boiling and it's evaporating and it's now rising up that fractionating column. But as it reaches the top of this column, other liquids in the solution at the bottom might start boiling and evaporating too, but because they'll be slightly lower, just slightly lower, as they rise up and follow the first one into the fractionating column, they'll get slowed down a little bit. And as it gets cooler, they might actually start to condense in the fractionating column and drip back down into the solution. So the fractionating column sort of slows down each liquid evaporating up and condensing through. And that gives us a chance to be able to separate all the liquids out and collect them in different pots. You know, I said that ethanol and water is the key example that your exam is going to use for an example of fractional distillation. Well, ethanol is alcohol, so that's what we're going to do today. We're going to distill some alcohol to make a really nice strong rum. So rum is just water, sugar and molasses. Mix it together really well and you add some yeast, which will hopefully ferment and make us some alcohol. Now, the making alcohol part is actually the job of the biologists, and you don't need to learn that about this for your GCSE, but the iGCSE biologists do have to learn about how to make alcohol through fermentation. So these biologists have mixed all this stuff together and they've gone, hey, here's this broth I've made with alcohol in it. Can you make it a lot stronger, please? Because the solution that they've given you has the water solvent. So the solvent is going to be, there's going to be a lot of it in there. There's going to be a lot of water in here. We don't want that. We want more alcohol in our rum than we want water. So you use exactly the same piece of equipment as we've just described, a fractional distillery. So a fractional distillation is what we're doing. And we're doing fractional distillation because water and alcohol, water and ethanol, have quite a similar boiling point. The alcohol, the ethanol, boils just slightly sooner than the water. So we stick our watery mixture into the bottom of our flask, we heat it up, and the first thing that's going to evaporate off is our alcohol, our ethanol. We're hopefully going to condense that in our condenser and siphon off, I suppose, distill off all of our strong alcohol and leave a lot of the water back in the flask. I would like you for exercise 4 to check out some of these homemade rum distilleries that are on the right and the bottom. Can you explain how they work? Now that you know how fractional distillation works, can you see where the condenser may be, or how they cool down the liquid, or how they heat it up, how they get evaporation, or where the fractionating column is? Can you see this in all of the homemade rum makers, homemade rum distilleries? Both of these are fractional distilleries, distillation equipment that people have made in their own homes to try and create rum. The only 2 parts of the pieces of equipment that you should need to know anyway are the fractionating column and the condenser. So although the heat source obviously in this one is the oven, and we can't see it in the one on the right. I haven't bothered to label them because you shouldn't need to know that for the exam. Similarly, the fractional flask, that sort of round ball thing, I'm pretty sure you wouldn't need to know that either in the exam either. So I haven't labelled that in the two pictures, despite the one on the right, it's going to be the beer keg, and the one on the left is going to be the kettle. That's going to be the initial flask that all of their ethanol and water is going to be in, that's going to hopefully separate out. So the one on the left, the fractionating column, looks like it's going to be this Coors Light sort of metal bottle. And their condenser is going to be this copper tubing that's curled round. They've made a little bit of an effort with this copper tubing. It's got a high surface area, so it's got a really good chance of condensing down. So I would have thought that they would get a good amount of liquid out of it. It would all condense. Whether it would all be ethanol, I'm not so sure. That fractionating column, we don't know what's inside, we don't know whether it's got anything inside like glass beads that would help, but I wouldn't have thought it would be the best thing in the world for making sure that they don't mix up too much. But whatever comes out the other end should be liquid, because it's got a good surface area, so it's had a really good chance to cool down. The one on the right, the fractionating column, they've done a little bit of effort here. They look like they've done some welding, so they've stuck this sort of homemade thick tubing into the opening of the beer keg. Again, we don't know what's inside, but it looks pretty similar to what you would get in a standard distillery for spirits, like gin or vodka or rum. The condenser, again, is a copper pipe coming out the side, fairly similar to what you would buy. In fact, they may have bought this actually and stuck it onto the beer keg. So yeah, you need to know what this equipment looks like. You need to know that it's exactly the same as simple distillation, but that there's a fractionating column stuck on there just to help those mixtures not mix up that have got boiling points that are close together. Right, you have now covered absolutely everything you need for simple and fractional distillation. Hopefully you've learned how to survive if you don't have any clean or fresh water, drinkable water. And you've also learned how to make a good rum, which the same would apply to a gin or a vodka. It really doesn't matter, a bit of moonshine. So I would like to do a learning check to make sure that you can apply all of this knowledge to what you may need to be asked in the exam. I would like you to fill in the blanks and use all of the words that are in purple to fill in those blanks. Pause the video, because in just a second I'm going to have to go through them together. So, distillation. Distillation is the process of separating substances. That's being a bit generic, a bit basic. It's generally separating out liquids, because all of that special equipment is really there to design to catch the evaporating gas and turn it back into a liquid. But yeah, distillation is a process, that would be better wording, a process of separating substances. Simple distillation involves heating up a solution. The substance with the lowest boiling point will evaporate first, the lowest boiling point. Do you know what, sometimes actually you'd be surprised how many people get that the wrong way round. So just get to grips with that. I know that normally the lowest thing doesn't go first, but it's arriving at the temperature that it needs to evaporate at quickest, because it's the lowest temperature. So the substance with the lowest boiling point, the lowest temperature at which it will boil and evaporate, is the one that's going to go first. The evaporated substance is then condensed back to a liquid in a condenser. Okay, so we've evaporated it, we've turned it into a gas with heat. Now we need to cool it down and turn it back into a liquid with a condenser. A common example of simple distillation is separating salt and water. This is the one they're going to ask you in your exam. I obviously can't predict hand on heart 100% that they may not shake that up, but in the history of past exams, the example for simple distillation is separating salt and water. Learn it. When the mixture has lots of fluids in it or has substances with similar boiling points, we can use fractional distillation. So fractional distillation is that slightly more complex one, slightly more equipment involved. There's only two: simple fractional distillation, and fractional is the slightly more complicated one that, yes, can separate out liquids that are all similar boiling points. It uses the same apparatus as simple distillation, but includes a fractionating column. Another crucial thing that you need to learn, the main difference is a fractionating column. It's very, very tall, and what we're going to move on to next, it's full of glass beads, cooler at the top, hotter at the bottom. That's how it works. That's how it tries to stop some of those ones with similar boiling points mixing in. A common example of fractional distillation is separating water from ethanol, or ethanol from water. And you need fractional distillation to do this because ethanol and water have a fairly close boiling point. Well done, you have covered everything. I hope that it's gone in. It's one of those lessons that there's a lot of different amounts of information coming from many different sources, so just spend a bit of time making sure that you've got it all in. Every week I give you an exam summary sheet. The exam summary sheet will contain everything that you need to pass that exam. I could just throw this at you every week because this is literally it. But the rest of the lesson is there to try and improve your understanding of everything on this sheet and also to give you a chance to practice it, so it actually goes into your long-term memory. But what I suggest to all students is every week you print off this exam summary sheet and you collect them up as the weeks go by, because these are going to be great flashcards, going to be great little recap revision tools for when you come to finishing the course and you want to revise for the exam. I don't go through it, I literally just place it in here every lesson. After the exam summary sheet every lesson, I always go through past exam questions. Doing exam questions, I cannot stress enough, is the most crucial thing you can do to pass your iGCSE with a good mark. Some of the questions are nothing short of bizarre, and you can learn that course content till you're blue in the face and do the exam and still not do that well. You need to know how they write their questions, so you're not scuppered by them in the exam, because they do tend to follow a similar path and you can often predict. So unfortunately, you're just going to have to work with them on this. We go through past exam questions every week in the lesson, and then we also go through them in some of the assignments, so you can tackle them without me in the background, and then I'll give you feedback and mark them, or I give you marks back at the end of the week regardless. So have a go at these past exam questions. They're slightly complicated this week. One of the questions is a continuation under the blue line, so everything to the left and under the blue line is one question, and then the other question is above it in the right, top right. Have a go, pause the video, and we'll go through them together. I hope you didn't find them too difficult. I'm going to start with question 3, which just happened to be number 3 on the past paper that I selected it from. I'm starting with number 3, which is in the top right. So, techniques used in the separation of mixtures. So A, B, C and D are 4 examples of ways that you can separate mixtures. Filtration and crystallization you wouldn't know about yet on your trial lesson. However, you should now know the difference and that they're there of simple distillation and fractional distillation. So the question is, for each separation, select the most suitable technique from A, B, C or D used to obtain the first named substance from the mixture. Okay, so each letter may be used once. Pure water, so we need to separate pure water, that's the first substance, from seawater. I hope you remember, please drum it in, salt water, seawater, simple distillation. That'll be what they ask, salt and water, simple distillation. It will always be simple distillation, so letter D. B, ethanol, from a mixture of ethanol and water. So we need to separate out ethanol from the mixture of ethanol and water. Again, I said it earlier, simple distillation is always seawater. Fractional distillation is always ethanol and water, alcohol and water. So it's C, fractional distillation. Now I want you to look at that was quite easy, that was simple, that was not a bad question. But look at the wording that they've used. They've said, for each separation, select the most suitable technique, A, B, C or D, used to obtain the first named substance from the mixture. The first named substance. So don't just go in guns a-blazing, because if question 3A had been seawater or salt from seawater, it wouldn't have been simple distillation, because we would have been getting the salt out of it, not the water. So even though I've always said to you that salt water is an example of simple distillation, it's only when you're getting the water from the solution. Remember, distillation is getting the liquid. It's trying to save that liquid. So if it had been salt at the beginning of that question, it wouldn't have been a distillation. Okay? They do this a lot. So make sure you read questions. Don't go in guns a-blazing and say, oh, little simple distillation, fractional distillation. Oh, great, I know this. Read questions. They will do funny things like that. Okay, so now I'm going to move on to the next question, which happens to be 2, and it's on the left-hand side moving down. The diagram shows 4 pieces of apparatus. Apparatus is the equipment that we use in science. Sometimes we call it apparatus. The diagram shows 4 pieces of apparatus used in the separation of mixtures, and they're labelled P, Q, R and S. The apparatus labelled S is used for what? It's given you some options, A, B, C or D. When we get asked questions on simple or fractional distillation, they will I'd be shocked if they weren't a question like this, a sort of A, B, C, D question. Any word question, anything that has long sentences to do with distillation will be to do with crude oil, which we'll tackle next week in our How to Make Rocket Fuel. So any of the basic questions about simple and fractional distillation will be revolving around questions like this, these sort of choose your option, multiple choice. So the apparatus labelled in S is used for what? Right. It's not going to be P or Q because we haven't really come across that today. I suppose Q, you could say we've got some liquid sort of evaporating somewhere. P, it looks like some sort of filtration thing, but we haven't been covering it today. But the bottom 2, R and S, look very familiar. So they're going to be either simple or fractional. So you need to remember that one key difference between simple and fractional distillation apparatus or equipment, and it's that fractionating column. Fractional distillation has a fractionating column, and in letter S we can see that. In R we can't. So R must be simple distillation, S must be fractional distillation. Moving on to question 2.2. Which method of separation should be used to obtain pure water from a mixture containing salt, sand and water? This is trying to scupper you. This is trying to trick you. Seawater, salt and water is always distillation. If we're trying to get the water from it, it's simple distillation. It doesn't matter if they've added sand. It doesn't, remember that dirty water in the pond, you're still distilling water. It's still simple distillation. So it doesn't matter what else they've added to it. If there's salt and water in there and they want the water, it's simple distillation. Well done. You have done an entire lesson with us. I know that was a long slog and I'm very grateful. I hope you did in little bursts rather than sat there and listened to me for the whole nearly hour. But just remember that when people are doing these GCSEs in a school, they will be having about 4 lessons a week over 3 years. So they are are doing much shorter little bursts over a longer period. So you can do the same thing. That's absolutely fine. Just play this video over a few days and just work through things at your leisure. But well done, you've achieved it. You've learned all about simple distillation, all about fractional distillation, and hopefully you've improved your pirate skills a little bit. So what we would normally do is you can complete your assignments as and when you like. You can complete as many or as few as you like. Obviously, the more you do, the better. And I'd like you to submit them by Friday at 6 p.m. So you've got about a week to, just less than a week to complete your assignments. And then if you have teacher support, I will mark them, or you've bought a marking credit, I will mark them. Alternatively, at the same point that I would mark them and return to you. If you haven't got teacher support, it's absolutely fine. I still send you the answers so you can work through them together. In the meantime, during the week, check out Facebook, check out Twitter. I will be posting constantly tips, videos, articles, activities to either cement that learning, put it in your long-term memory, or to work on it if you have developed an interest in whatever we've been talking about. And also during the week, feel free to ask questions in the Facebook group or the online forum to either your fellow students or me, and I will happily answer as many as I possibly can.